All right, so, well, welcome back to part 3 of my little series of lectures. And after yesterday's lecture, where I talked about this rescaling of some interaction term in the Hamiltonian, there were a lot of discussions and a lot of questions, which is always very good and enjoyable because, I mean, this way I think we're making progress in the understanding. But I also thought, since there were so many questions, I will try to use just 2 or 3 minutes of this lecture for a quick recap, including some comments that maybe clarify to everyone what I was asked by people yesterday. My suggestion, however, is that we don't start another question session on this topic during today's lecture. If you have further questions after the lecture, I'm here for the whole afternoon, and you can poke me and ask me questions. But that I try to give that little recap, and then we move on to new material. And then for the new material, of course, you, as always, you're very welcome to ask questions during the lecture. But for the little recap, we do that afterwards. Good. So the little recap is about this factor curly n that I inserted into as a prefactor of the interaction term in the Hamiltonian. And the first comment I wanted to make is a remark on the name. So adding a prefactor in a long-range Hamiltonian, and I think I didn't mention this last time, is very often referred to in context with the name of a mathematician, Mark Katz. And so introducing this factor in the long-range Hamiltonian is sometimes called the Katz rescaling or Katz prescription. And I mention this just so that you can make contact with literature where you might find that name. I was always not so convinced that it's a good name, because in the papers of Katz where I looked it up, he does something with Hamiltonian. He does a modification, but not the one that I introduced here, actually. But this will be of no further concern here. So the most important message here that I want to summarize is I discussed very briefly 3 different options that we might have in proceeding. And the first one was no introduction of that prefactor. And I showed you that you may have divergences when you take a thermodynamic limit. Maybe before, now these comments all refer to situations where I want to take the thermodynamic limit. Whenever I stay with finite systems, I think my main message here was you do whatever you want. Meaning, you can introduce this prefactor, you can leave it out. There will no be substantial difference. You can rescale between results that you obtain. You do whatever seems more convenient or makes closer connection with existing literature. So there's no strong preference, as long as you stay at a finite system size and you don't compare different system sizes. The moment you want to compare different system sizes, like in finite size scaling, you may consider introducing this factor. If we want to do a large system limit, a thermodynamic limit, no introduction of the prefactor will lead to divergences. So it's in general not such a good idea. And what I had as the third option, which is modifying the free energy to the one with that inverted head that I was using. So fiddling with the definition of this of the free energy gives you results in a finite free energy, so it gives a finite quantity in the thermodynamic limit, but interesting physics is lost. So there is no formal problem here in terms of divergences, but we get less interesting results, and I'll comment in a minute in what sense the other ones are more interesting. So this is also not a great idea, and I don't recommend it. So this using this prefactor is a good idea for the situation I consider here. So you want to take a thermodynamic limit, and this prefactor is useful, as I discussed, for studying, as I did here, free energies, equilibrium statistical physics. That's a great thing to do. It's a good choice. I will show you in tomorrow's or Friday's lecture a situation where we do some other physics. We do not calculate free energies, but we calculate something else, dynamical quantities. And I will show you that there are situations where no prefactor is not a good idea, but the prefactor is also not a good idea, but some other prefactor is a good idea. So in the sense that you may have to adjust what you're doing here depending on the quantity that you're looking at. There's not one recipe that works for everything. This here works for very many interesting things that you want to do, and you see it mostly in the literature of long-range systems, but there can be exceptions where some other prefactor is giving you the good results. So you will have to look at your problem, and you will see in the example that I show you how we realize that neither of this and this is a good idea, and we need to do something else. So we see this from the results we obtain. And the final comment I want to make is on the interpretation of the results. So assume now that we have calculated the free energy with respect to the rescaled Hamiltonian in the thermodynamic limit, because as I argued here, that would be the good choice, the good thing to do. And I'll here use only beta, the inverse temperature, as an argument here. So we have this free energy of the rescale Hamiltonian as a function of beta. And now we do this for some long-range model that we find interesting, and let's assume we find a phase transition at a critical inverse temperature BC. Now what I emphasized in the last lecture that we want to, we may want to translate the result we get for the rescaled Hamiltonian to the non-rescaled Hamiltonian. So what does this mean for the Hamiltonian without the rescaling? So if you look in your notes of last lectures, you will see that when comparing the free energy of the tilde Hamiltonian to the one without the tilde, we had to rescale the inverse temperature also with that prefactor. So finding a free energy here with a phase transition at that point will correspond to finding in the free energy without this quantity, if it existed. So I mean, we have to be cautious here what exactly I mean with that. With this rescaling would correspond to a critical temperature of beta C, now I have to think, times n, so that would correspond, this here goes to 0, and so inverse temperature, critical temperature goes to 0. Yes, that's correct, yeah, good. So this is of course infinite in the thermodynamic limit, so, but this tells us kind of that in the non-rescaled Hamiltonian, the phase transition is pushed to infinite temperatures. Now, what do we want to do? What do we mean when we use the thermodynamic limit? We use this as an idealization. We want to learn about finite but very large systems, but not really about the infinite system. So this would tell us in the unscaled model, we have, for finite systems, you don't rigorously have a phase transition, but you have strong precursors of a phase transition, like a very sharp peak in a specific heat or something like this. You will have this for finite systems. For a finite system of size n, you will have this at some temperature. For a finite system of double the size, you will have this at a larger temperature, and so on. So this is the statement. This is what we learn about the unscaled system by finding a phase transition at a critical temperature here in the with the rescaled Hamiltonian in the thermodynamic limit. So I hope that this little explanation, which is based on the questions I received yesterday, helps a little bit in understanding what we want to do here, what the result means, and when not we may want to use this factor. All right, I'll stop here. After the lecture, please feel free to come with as many questions as you like, but then for today, I would like to move on to the next big chapter of this little lecture series, which is equilibrium physics of quantum long-range systems. So this should be 5, which is equilibrium physics. So what are the main topics of the section for equilibrium physics? We want to look at phase transitions, and I'll go with you through one example of a thermal, like a finite temperature phase transition. And we'll see that long-range interactions can significantly change the properties of the phase transition, and it can also in some cases induce a phase transitions in systems that with short-range interactions don't have a phase transition. So it can really dramatically change the properties of systems, the presence of long-range interactions. And then we'll also look at quantum phase transitions. And I'll go through an example with you where we'll see that universality classes, like the critical exponents that govern this quantum phase transition, are strongly affected by the presence of long-range interactions. So these are the main topics that I will discuss today and maybe part of tomorrow's lecture, and then after that we move on to non-equilibrium physics. A remark on what I'm going to do now. So in the spirit of, like I told you before, I'm going to try to look for the model where I can show you the simplest calculation that already reveals the physics that I consider interesting. And sometimes someone may think, oh, but this is isn't that too simple? Isn't that simpler than we should go? But I think there's something interesting to see and learn. And then when we have gone through an explicit example and have some results, I'll give you comments and links to the literature where the more general cases or different systems and so on are considered. So that's the plan. And the main, so when I look at thermal phase transitions, the main simplification that I'm going to use to be able to do a simple calculation that I can easily do here on the blackboard with you is to use the case alpha equals 0, so the all-to-all interactions. But I will comment on in what sense results that we find also apply for other values of alpha. So 5.1 would be then thermal phase transitions in long-range systems. And the main simplification, so for simplicity, alpha equals 0, and generalizations will come later. I'll do this for so the case alpha equals 0, I will also sometimes call the all-to-all interactions. I think that's also a common name. So I will consider an all-to-all Hamiltonian. I'll not use exactly the Ising model that I discussed in yesterday's lectures, but a more general model, look at a special case there, but tell you in what sense you extend these calculations to the transverse field Ising model that we looked at yesterday. So the Hamiltonian will be 1 over n prefactor. So this is for alpha equals 0. This is the rescaling factor that I just discussed. Then ij from 1 to n. And then, at first, to have a more general class of model that includes the transverse field easing model, I'll introduce XX coupling here, but also another term with YY coupling. Oh, sorry, this must be a J. And a term with ZZ coupling. It's J. And the usual field term for which I chose the X direction. All right, you can of course easily recognize that for what I have to say, lambda x equals lambda y equals 0. We have the transverse field easing model from yesterday's lecture. So it's included in this class. I will discuss with you a special case. You will immediately understand why the special case I look at is even simpler in calculations, but I'll also tell you how you generalize this. So what we'll be looking at is sigma x equals sigma y equals sigma z to some value that I'll be calling j. And this is then the all-to-all Heisenberg model. And now I've introduced so many simplifying assumptions that we really can make a fairly easy calculation and get some results. And the first step for a simplification that I'll be using is I'll define what is called collective spin operators. So they are S. Well, I call them S alpha, where alpha is x, y, or z, so one of the indices, and it's just 1/2 sum over all the spins, sigma I alpha. So I either sum all the x components, or all the z components, or all the y components, and I get this collective spin operator. So alpha is x, y, or z. Sorry? Because the sigmas are different, so I want these to have spin operator properties, and for a spin 1/2 operator, you will also have the 1.5 factor in front of the Pauli matrix. So I just keep this so that these really deserve their name as collective spin operators. So the Hamiltonian then, you can very easily see that I should get to the following form. Okay, so this is what I'm writing down now is not yet for the Heisenberg, but this is the general case. Let's write it down anyway. Plus lambda z is z squared. So these double sums turn into squares in the collective spin operators, minus 2hs x. Yeah, and the fact that one can write this in this form, this is of course specific to all interactions, and it would not work in the same way for other values. Sorry, this one here? No, sorry, where did I make a mistake? So these are squares, and this is a z. So the z, I had my z has a little horizontal. All good? Okay. Right, and now the important point is that these collective spin operators deserve their names. And by this I mean that if I write down the commutation relations of, say, S alpha and S beta, I get I, the complete antisymmetric tensor epsilon alpha beta gamma S gamma, so I get a spin algebra. And this, of course, makes my life a lot easier because I know properties of these operators, and this follows directly from the corresponding commutation relations of the this Pauli matrices, which would be 2I delta ij. Okay, this is the complex I, and these are this is the I index. I hope you're not too confused by my bad notation. And then, of course, we get the same alpha, beta, gamma, sigma. Yeah, sigma I, gamma, that way. Yeah, so now these here are angular momentum operators, and the spin value of these will be n half, because we have n spin 1/2 that we are combining here. Well, this will be the maximum angular momentum. So the point here is we know that the angular momentum eigenstates are eigenstates of the say S squared and Sx. I will use here for simplicity. Angular momentum eigenstates Sm that you've all seen in your quantum mechanics courses are simultaneous eigenstates of the S square operator. And well, I know it's conventional to say the other one here is Sz, but I will say I will use Sx. It's just a rotation of, it's only, I would like this guy here to have Sm as an eigenstate. So this is just, it's not the typical convention to have Sz as the one, but it really doesn't make a difference here. And now the choice of the Heisenberg model that I said I want to use, so where all the three lambdas are equal, of course, makes the important difference, because now, well, if these three are equal, then we get, well, what is it? Then I call this J, and then we have S squared minus 2h Sx. So, and at this point, someone might say, but no, now you made it really simple in the sense that we have, we know simultaneous eigenbases of the Hamiltonian here. But look, a simplification is too simple when you lose the interesting physics with it. In this case, I claim now that I don't lose the physics that I'm interested here for this purpose, so I'm very happy with my simplifying assumption and the fact that I can more easily do the calculation here. And what is the calculation? I would like to calculate the central quantity of equilibrium statistical physics, so the canonical partition function. So we want to do Z beta h, which is, as you all know, the trace of e to the minus beta h. And then the trace we can always do in the basis of our choice. So, and the basis of our choice will then of course be the SM basis that I wrote up here. And so I have to sum over all the possible values of S. Leave a little space here in your notes because we need to introduce something extra. And then the M values will go from minus S to S. And then we look at the matrix, well, for the trace, we look at the diagonal matrix elements of the Boltzmann factor. So we'll have e to the minus beta h s m. And now I left here a little space for something that I'll explain to you where it comes from, but this would take me probably an hour or so to really derive with providing background of it. And this is here an extra degeneracy factor which depends on S comes in. So where does it come from? We said here that, so what we have is we have many spin 1/2s and we combine them together into longer spins. And then there are multiplicities in how many ways you can combine these into the longer spin. But the number of the multiplicity is really not so simple. It's not like you think, oh, I take these spins and I flip one or something like this, like in a classical picture. It unfortunately does not work that easily. But there are the degeneracies for deriving them. This works by using group theory or representation theory, where you will have to count the number of irreducible representations of certain groups and how you split a group into the subgroups and so on. And the derivation is done, or the one that I have seen, and by a method called Young diagrams, which you might have seen or not, but this is something where, so I don't want to get into this here at this point. I think you can get an idea where it's coming from, and I can give you a reference where you find more details about this, but it's not something that I'm going to derive here. So there is one part which I consider non-trivial, but it has also been known in the literature since, or many, many decades. So at the first half of the previous century or something like this. So it's a well-established result at the same time. So this GS, one way of writing it is this here, and then we get n½ plus S plus 1 faculty and n½ minus S faculty. It looks a little bit like a binomial coefficient, but it's not quite. And it can also be in another way written as a difference between two binomial coefficients. But we're only going to need this form here. And the paper where I first saw it, and where actually the calculation I'm doing today with you is also sketched, is in a paper by Scharf, sketched because in 1972 apparently people could write 1.5-page papers. It was still a thing. I haven't seen one in a long time otherwise. So the guy's name is Scharf, and it's physics letters 38A 123 from 1972. And there's a newer one where this is also featured and explained also in a bit more modern language by Babst and Simerian. And this is in the journal JSTAT, so this Journal of Statistical Mechanics from 2012, and I think with this information you'll easily find it. So well, I think you at least got an idea what this, where this GS comes from. It's about degeneracies, and degeneracies also in this type of formula kind of play the role of a density of states. So yeah, it's counting states and multiplicities. So think of the logarithm of this will be at least closely related to the microcanonical entropy of that object that we are calculating at the moment.
It's a GS, like, isn't it like for a given value of S, how many ways I can get a given value of M? Is it capital M? So there are many ways, I mean many...
No, this is multiplicities of S. This is
no,
a same...
S.
Yeah.
Oh, achha, how many
No,
ways I can combine the spins to get a given value of?
Yes, of S, yeah. The M's come only in here on that side, and this is for a given S, you know what the M value are as the usual minus S to S, but this is a different object.
Okay, thanks.
Right, so at this point I make a comment related to what Leah said in her lecture at some point, that when alpha is 0 or close to 0, that we essentially get to a single particle problem instead of a many particle problem. And I wouldn't agree with this statement in full generality, because you can still, for that many, if you do dynamics, for example, you can have that Hamiltonian with all-to-all interactions, but you flip a single spin and you will see something where something is spreading across the lattice or something like this. So not everything looks like a single particle in there, but if you do a calculation like this equilibrium calculation, this is, I mean, now we are essentially dealing with a system that, apart from this multiplicity factor, looks like you're looking at the partition function of a single large spin. All right, so this is our remaining task now, is to evaluate this formula, this expectation value here. And at this point you see, of course, that why the choice of this Heisenberg Hamiltonian makes our life so simple. So now the Sm is an eigenbasis of the Hamiltonian, and we can directly evaluate this expectation value. If it's not an eigenvalue, so if we do another model like the transverse field Ising model that we may find more interesting for some reason, then we cannot do this directly. But still, there is a, I would say, reasonably simple way to evaluate this. And there's also a reference I can point you to. This has been done by various people. Because we consider the limit where S can become very large, one can do something like a semi-classical approximation. You're considering this S, dealing with it essentially as if it would be a very large classical spin. So you write this Hamiltonian in terms of classical angles of some large spin, and you get the same result that you can also, with a lot of more work, prove when calculating the exact expression of this thing, which can also be done by a high-dimensional saddle point approximation of some. So then it becomes a messy thing, but still there are mathematically rigorous results for computing results like this with non-commuting terms. So there are different levels of complication and of rigor that you may have, but so we don't need that H commutes, that H has Sm as an eigenbasis. It makes life simple. We can do a hand-waving calculation otherwise, or we can work a lot and do something rigorous, and the results coincide here. All right, so yeah, let's get to the calculation of this thing. Well, it's of Sm e to the minus beta h Sm. We can, of course, evaluate the Hamiltonian accordingly, and we straight away get an exponential here. So the prefactor 4 beta j divided by n, and then the eigenvalue of the s square operator in the Hamiltonian gives us the usual s times s minus 1, sorry, s plus 1. And the evaluation of the x component, we said x component corresponds to our quantum number n, so we get 2 beta h m. Right, that's nice and simple. And then we can write down the full partition by plugging this into this expression and also this factor into this expression. And at this point, I thought that I spent all my lecture writing down these long expressions where I only want to explain you the principles of how you continue with the calculation. So I prepared a little slide for that. So the top line that you're seeing is just this formula here, plugging in the GS and plugging in the expectation value that I calculated here. So nothing else has happened yet. And what I want to do now is I want to take a thermodynamic limit. The main reason for this is usually that it makes expressions simpler. I mean, it's not that people don't like working with finite systems, but it is a significant simplification, and we will have methods that we can use for simplification. Here, Justin, this is maybe not in one, maybe not immediately to see, but these exponentials can be summed up, and so the sum can be performed, and we get this ratio of hyperbolic sine functions. But I'll not do this calculation here. And then we plug this into the expression for the canonical free energy density. So we have this limit n to infinity, a prefactor, and the logarithm of the partition function. And what I also did in this expression, that I changed from the sum into an integral. Integration goes, the sum was up to n half, integration goes to 1/2, and the n here I got as a prefactor for the integral. Otherwise, nothing has yet happened in this formula. And what I'm going to do now is with this unpleasant looking expression here, with these factorials, I will, because we are doing a large n limit, I'll use Stirling approximation, so which I've written down here. So the ln n faculty will be n ln n. So n is now not necessarily this n, but anything large. So I can apply the same thing also to these terms here. Oh, I forgot to say that the s is now just little s is capital S divided by n, but we had this in yesterday's lecture already. So I'm going to do Stirling approximation, and there are a few terms where I can essentially already read off that they are not going to be, they're not going to survive the thermodynamic limit. Just a simple example. This one here in the logarithm will be something that is linear in n. I take a logarithm and divide by n here, so it will not be a contribution that survives in the thermodynamic limit. And the same reasoning can be done for these for a term like this, where we will have here terms that are that are dominating over these here. So this one can be neglected and that one as well. This can be done more carefully, but I think I'll keep it at this level of the discussion here right now. We will lose these terms, and the remaining ones, plus Stirling approximation, we will all write into one formula. And there's one nice thing happens, that in the Stirling approximation, all the terms of the order of type n ln n, so also those here containing s and so on, all those that are larger than order n will cancel out. So we all lose them, which is a very convenient thing. And we end up with an expression. I put now everything into one exponential, and we have this one n here at the front. The rest is all n independent. From this, when doing this step, essentially one sees which of the terms are falling out, because some of them will have a 1 over n prefactor or something of the sort, or they will not be in the exponent with a linear n dependence, and therefore these will be cancelling out. So this is now the integral we have. This is really just a relatively basic algebra and neglecting some lower order terms in n to do this calculation. And now comes something more interesting, and this is something if you, yes please. I'm not, so I didn't understand. Can you please repeat? Yes. In the second term, like in this one? In this?
The denominator again half minus s. Saying when s is close to half, then you do the Stirling approximation and not. Because that would make the term small, right? I think you can do it.
Yeah, so I think if you, I think the logic of the calculation here goes as follows. If you find that in the, no, hang on, let me think. So if I understood correctly, this is so if it turns out to be a small term, then Stirling approximation may not be so work so well, but at the same time you will get a term that is not contributing in a relevant fashion in any case. So you're not, in the sense you would not be so worried about the approximation error you're making. I think that would be the reasoning here at this point. I'm sure there's a better way to explain this than I did just now, but I think this at least should save the argument for now. Anyone else with a better comment on this?
Stirling approximation works for even small values of n. Even if you take n6 or 7, the approximation is approximately, close to 99%. So in a sense that, as you said, what is, if you do the scaling, when s is like 1 over 2 minus 6 divided by n, that's your
maybe in this direction, maybe the argument just goes, I mean, sure, if you say s is exactly 1/2, then at exactly this point you may be in trouble. But otherwise you go a little bit away and the n will also dominate over that term, and then you'll be fine. Okay, I think you saved me, thanks to everyone who contributed. I think this is how the reasoning goes. What I wanted to mention now, we end up with this integral here, integral over some exponential function where the large parameter is in the exponent. And I assume many of you have seen this before, that this is sometimes called, or it's a kind of integral that can be treated asymptotically by methods that were developed by Laplace a long time back. And there's a bunch of methods that are all related to the same idea of Laplace, and they go by method of steepest descent, saddle point approximation, and so on, and Laplace evaluation. And the idea is always, or the upshot is always that when you have an integral of that sort, the exponent, or this exponential with an n prefactor, will lead to a function that is very much dominated by the maximum, and in the infinite n limit, it is really only the value at the maximum that will contribute to the integral. And this can be proved rigorously by deriving upper and lower bounds. So this is a proper mathematical result, not just hand waving. And what we really can do in this expression now is the value of the free energy is, because this n and that n cancel, is pretty much is essentially equal to the value of the exponent at its maximum. So this is what I've written in the next line. So, well, I put the beta prefactor and the minus sign on that side. When doing the maximum evaluation, this n and this n cancel each other. The logarithm and the exponential pretty much cancel each other effectively, and what the remainder is this expression here evaluated at the value s0, which is the value at which this function here has its maximum. And now the only remaining task is finding the maximum of this exponent, and there's a little bit of algebra involved. If you want to redo the calculation, there's the one trick for finding the maximum analytically is to do a substitution of the parameter s to a function which is 1/2 hyperbolic tangent of alpha. So I shouldn't call it alpha, let's call it a. So that's not our alpha. So we introduce a new variable a. You can search the maximum, because this is a monotonously increasing function. You can search the maximum in respect to this variable, and the calculation becomes doable, and you end up with you can determine the maximum analytically and end up with this canonical free energy density, which I've written here. I'll not discuss the physics of this formula now. So this is the formula, and the alpha 0 is the solution of this quantity here, down here. And why I wanted, so the aim of this part of the lecture was twofold. So first, I wanted to give you a flavor of at least a few tricks that are used, which is the introduction of collective spin operators for alpha equals 0 models, and then a little bit of an idea how the simplest possible calculation of such a model goes. And but mostly I wanted to point out some properties of the result that we obtained. And the important one I want to stress here is that this result that we obtained by a calculation for that model is the same that we would have obtained by using the mean field approximation. So mean field approximation usually means you have a model that is not all-to-all coupled, but you have some spin model, say a spin Heisenberg model. It's too hard to solve for some reason. You say, I'm not going to be able to solve this model, but I hope to get some idea about the physics of the model by doing a mean field approximation, which usually means in the Hamiltonian of the spin-spin interaction, I replace one of the spin operators by its expectation value and then solve self-consistently. I'm sure you have seen this at some point. And this is an approximation, and it's known that for some systems it can be quite bad. Especially one-dimensional systems, it may fail badly in terms of its predictions, and for some other system it may work quite well. Three-dimensional magnets, for example, it works quite well. And here we find that if we have a very long-range system, it works perfectly. So we get the exact, if we would not have done this calculation, but a mean field treatment right from the start, we would have gotten the same result. And I think this is a remarkable observation, and it's also the reason why people would call the class of the all-to-all models sometimes mean field models, because, I mean, first it resembles a mean field description. Everyone sees everyone else, and it also has mean field as its exact solution here. Oh, can you speak up? I didn't.
You are taking alpha equals to 0.
Yes.
Very fast moment.
Yeah.
That
Well, so no. For me, taking alpha equals 0, this is my definition of the model. And so the mean field, look, there's different names in the literature. Some people would call this mean field interactions. I somehow prefer all-to-all interactions to distinguish the choice of interactions, like what model do we look at, from mean field, which for me is an approximative method for calculation. So but this is my personal choice of words at this point. I use the word mean field for a method where you approximate your Hamiltonian by replacing an operator by its expectation value and solving self-consistently, as you certainly have seen at some point. And the interactions here, some people, because of similarities, would call them mean field interactions, or say this is a mean field assumption or something, but I would say this is all-to-all interactions. But still, I would keep these things separate. I can have a spin model, and I do a calculation of the model like I did here, and I find this result. I can take a spin model, maybe not with alpha equals 0, but with some other value of alpha. I do a mean field approximation, and I get the same result. If I do this for a nearest neighbor model, which still many people do, I get a result that is an approximation, maybe a good one, maybe not, but it's not exact. If I would have done the mean field approximation for this model, I would have gotten the same exact result.
This is the exact result, right, for this model?
As well, except of mistakes I did in the derivation maybe, but otherwise it's exact, yeah. This is the exact result. There was no approximation. So what looked like neglecting terms and so on, this was all in the n infinity limit. These are exact results. The Laplace evaluation that I showed you, the Laplace method is exact in the large n limit. There's no approximation. For this model, we have not done the mean field calculation here. We have done the exact calculation. We could have done, starting from the Hamiltonian, the mean field calculation, we would have gotten the same thing. That is like one of the main messages here at this point.
So but the mean field to apply the mean field approximation, that could have been the straightforward thing to do. Then why go through this? It's an all-to-all model. So mean field is the first thing that one would have done. No?
An experienced researcher, yes. But I think the message at this point would be, how do we know? Look, you have learned at some point that for these models you can do mean field right from the start and you get the right thing. But at some point you have to learn, right? That is the case. And this was the attempt to convey exactly this message. I think it's not clear from the outset. And in fact, it's something that also, to prove this in more generality. So I was still looking for the paper where for pretty much any class of model you show that mean field is exact. I don't think it's that easy. You can do something for some classes and so on, but I think it's the general belief that you have an all-to-all model, mean field gives the exact results. I don't know of any counterexample, and at some point when you have worked with this for some time, you take it absolutely for granted. So, yeah. Yes. Yeah. Doing a mean field, so the mean field approximation gives different results for different types of systems. So mean field for an Ising system and mean field for an XY model and mean field for something else, they do not give the exact same result. But for the Heisenberg all-to-all model, you obtain the Heisenberg mean field approximation result. for the Ising all-to-all model, you obtain the corresponding mean field result. So you have to do the mean field approximation for the same type of model, which usually means that your model must have the same symmetries as. So Heisenberg has a full rotational symmetry of the spin, if you speak classically or something, or Ising model has a Z2 symmetry, so you need to have, well, the word of the business is the order parameter is of the same symmetry, has the same symmetry as the model you're considering. So you have to do Heisenberg approximation for for the corresponding model that you're interested in, that is your all-to-all model. Right, so I would now continue if there's no immediate questions. Yeah.
Just for the example for systems where lambda x, lambda y, lambda b.
So, of course, so you not mean systems in the sense I wrote down the transverse field Ising, which is my system. No, but seriously, there is, look, no, I'm not good at naming materials, but if you find a lot of literature where people say if you have some anisotropy in the crystal, then also spin-spin interactions get some anisotropy. And there's many models where people would say we have layers, and therefore we have the X and Y coupling is the same, but the Z coupling is different. There's models where in the crystal, those with different kinds of atoms, those atoms whose spins are relevant essentially form 1D lines with ordered, where the spins only couple along the line, and then you get, so there is many materials around where people say in this material the spin physics has this anisotropy, and therefore this and that class of model is realized. Yeah, but you searching with this, you easily find many examples of that. Okay, a few comments. The first one is all-to-all beyond Heisenberg. So we keep the alpha equals 0, but we don't do the case where all the lambda, x lambda, y lambda, z are identical. Well, the Sm is not an eigenbasis. As I said, there is a paper with a rather simple semi-classical approach that can easily be followed and reproduced and applied to other models as well. Semi-classical approach, and the authors are Del Rey, Tosatti, and Fabrizio. And it's PRB 2016. And there's old rigorous results by Tindemans and Capel. From the old Physica Journal 72, and it's 1972. So this here is really taking the whole partition function and doing upper and lower bounds on that are shown to coincide with the mean field solution. So this is hard stuff to read. If you want to get results, I would not recommend this here, but rather following the method in that newer paper here. If you want to be rigorous, then you have to go the hard way. Second comment is a very interesting one, I believe. What happens for alpha larger than 0, and I'll tell you about results that are for alpha between 0 and d, there exist, at least for some classes, but fairly broad classes of systems under fairly general conditions, proofs of exactness of mean field. Which I think is also a remarkable thing to observe, that there is a whole range of values of alpha where mean field gives you the exact solution, and it goes up to the dimension of the lattice that we're considering, D. And one version of these proofs that I find the most readable is by Takashi Mori. And it's also fairly recent. It's a PRE from, what is it, 2012. Well, recent on my time scale. There's a side comment I want to make here. So in this paper by Takashi Mori, he shows that for all these values of alpha in the class of systems he's considering here, mean field is exact for these values of alpha, except in situations where you have a phenomenon that is called non-equivalence of ensembles. And I'll not go into detail here because Alessandro Campa confirmed to me that he'll discuss non-equivalence in his lectures, so you will learn about this here. The upshot is that microcanonical and canonical calculations, even in the large n limit, will not give you identical results. And the one important point to know when to worry, so only when you have a first order phase transition canonically, there is a chance of having non-equivalence of ensembles. So if you do a calculation canonically and you find there's no first order phase transition, you don't have to worry about this phenomenon at all. And otherwise, it's something that can happen in long-range models. So this is a long-range peculiarity that it can occur in quantum and in classical models. So there is, one can do a not much more complicated than that calculation with a little bit more involved model that also contains quartic terms in spin operators, and arrive at something that shows non-equivalence of ensembles in a quantum system, but I'm not going to go in this direction here.
Because this Takashi's paper, is it the classical setting or is it quantum setting? In the classical,
Yes, this is the classical paper, yeah.
so quantum, there is no proof of exactness.
I don't think so, yeah. But I mean, sometimes there are results like this a little bit hidden somewhere where someone at least considers a certain model and shows it or so, but really for broad classes of systems, I don't think so. Yeah.
He also has a follow-up paper in 2014.
And
Same topic.
yeah, but is this also classical?
Yeah.
Okay.
But I think he incorporates disorder into the picture.
Mm-hmm.
Discusses later.
All right, I want to finish this section on thermal phase transitions with some more comments on the general picture of what we find and what we can expect. So let's put this as comment 3. Now I'm just stating some results from the literature that are general or fairly general for long-range systems and related to thermal phase transitions, just for you to get a broader picture when long-range interactions lead to important changes and when they don't. So now I'll be a bit more specific and show and discuss results for our favorite model, the 1D transverse field Ising model, with alpha, well, something larger than or equal than 0, and discuss what introducing long-range interactions here does to the system. And the first result I want to mention is that there does not exist a phase transition, a thermal phase transition, for example, for the short-range Ising model. This is in 1D, and it's something like at least fairly common that 1D models don't show thermal phase transitions with very, you need to construct something fairly artificial to get a phase transition with short-range interactions in a 1D model, but long-range interactions will help us in that way. So there doesn't exist a phase transition, a thermal phase transition, so at T larger than 0 for all alpha between, for all alpha larger than 2. And there exists a phase transition at T larger than 0, correspondingly for alpha, in that interval, this is an equal. I think there's something interesting to remark in terms of the mean field approximation. So when we take the transverse field Ising model in one dimension with any exponent alpha, whatever that exponent is, the mean field approximation, this approximation method, will give us the result that essentially I've shown here. I didn't show you the transverse field Ising case, but something very similar. So when I take the 1D Ising chain at some large value of alpha, the mean field approximation will tell me there is a phase transition, but the real model doesn't have one. So mean field in low dimension with short-range interaction can fail badly, and it tends to over-predict the presence of phase transitions. It usually does not predict less phase transitions than there are, but more phase transitions than there are. So this is the warning. Mean field can go very wrong, but we also learned, of course, that mean field can be very right. And the interesting point here is that I think the observation that long-range interactions can stabilize an ordered phase. So the ordered low temperature phase to which we have a phase transitions in these models, we don't have without long-range interactions. And I think it's kind of physically intuitive, because the ordered phase is like, say, all spins pointing in the same direction, and the long-range interactions typically enforce, when they are ferromagnetic, that spins tend to point interactions also over long distances. So the creation of long-range order and long-range correlations and so on is enhanced. So it sounds also physically intuitive, I would say, that long-range can stabilize the ordered phase.
So here is a distinguishing between alpha less than 1 and alpha between 1 and 2, right? I mean, the so-called weak long range.
This is the next line I'm going to write. Yeah, exactly. You're perfectly right. So there is a regime where we find mean field critical exponents, and in this model, if I didn't if I didn't look it up incorrectly, it was for alpha between 0 and 1.5. So critical exponents, of course, as you know, usually determine universality classes, and there is the mean field universality classes where the mean field exponent alpha is, for example, 0. That's not our alpha, that's another alpha. And beta, I think, is 1, and so on. So there is a certain set of values. And for all alpha in that range, we have the same mean field exponents. And a plot, well, for some other exponent, for example, gamma, which is the one that corresponds to the magnetic susceptibility, if I remember correctly, in a model as a function of alpha. Same exponent for alpha between 0 and 3/2. So we have some value of that exponent is always constant up to that point. Then from there on, it will change linearly with alpha. So it does something like this. And at 2, it stops because there's no phase transition on that side. So why did I want to show this? This kind of behavior, which I here told you for the 1D transverse field Ising model, it shows some typical features of long-range models. That is, that there is usually a regime of very long-range systems where, well, we know mean field is exact, so also the mean field exponents must be the correct ones of the phase transitions. It can extend further where mean field is not the exact result, but the exponents still are not changed. But a very typical feature for long-range interactions is that there is a regime where something very unconventional happens. That is, universality classes, which usually means fixed exponents for a broad class of models. They are not so universal in the sense that they depend in a continuous way on the parameter alpha. In most other types of models that you would looking at, you have this set of critical exponent and then another discrete set of critical exponents for some other model. But that critical exponents change continuously with some parameter is not so super widespread, not so super common, and this is something we'll have in these models. And we'll also see that when we're going to go to the study of quantum phase transition, which is the next topic, that a very similar behavior like mean field region and a continuous change of the exponent in some region will also be realized. And this here, I think that's just an interesting historic remark, the study of the existence of a phase transition in long-range Ising models, the classical one, but for this question, this does not make a big difference for a thermal phase transition. Goes back to Freeman Dyson, who got interested in these models in the 1960s. So this is from 1969 in Communications in Mathematical Physics, and a number of follow-up works. Yes, yeah. So this is why the argument I try to make, saying that if we have this long-range order, say ferromagnetic, and the long-range interaction is of that type, it tends to stabilize exactly that. It gets more tricky already for antiferromagnetic, and then for other types of phase transitions, like topological ones that do not have long-range order at all, the whole mechanism doesn't seem to work. So there's we'll see a model like just now or beginning of next lecture where that has a topological transition, and there's no way to stabilize it by going to long-range interactions. Yes, please.
What kind of arguments do people give to explain this kind of behavior, continuous change?
This change here, I don't know of a physics argument, but this is, so what Dyson did, that he constructed models that are very similar but more solvable than the transverse field Ising model, and argues that the difference of the critical behavior is small and in this way gets to a result like this, and otherwise there's renormalization group calculations of the critical exponents of such a model where this is the outcome. But I wouldn't know of a like a physics argument that would help there. And I'm also on the renormalization side. I mean, I know that some people can think in flows and fixed points, but I'm not so good at that either. So I wouldn't come up with an argument in this language as well. So, yeah.
When you're saying long-range stabilized moderate phase, do you mean moderate in the sense of ferromagnetism, or does it include also needle order?
Does it stabilize antiferromagnetic order?
With long-range interactions.
Yeah.
It's very complicated. It's frustrating.
Yeah. This is what I'm thinking, because I mean, the one atom would maybe be in favor of the ordering as you have it at the moment. Oh no, but it's only because no.
It's frustrating. I mean, if you have antiferromagnetic interaction, this guy would want to.
Yeah. No.
Not align. Sorry. I mean, nearest neighbors you do this, right? But if it's long range, so how do you know this guy is placed?
No, but if the long range also favors, if the long range is such that you want your next nearest neighbor to be of the opposite sign.
Yeah, exactly.
So,
Frustration.
no, I don't think so.
Why not? Because this guy.
So you would always, the long range interaction would be, I want my nearest neighbor to be opposite, and I give some strength to it. And I want my next nearest neighbor to be aligned, and I give some other way to it.
Taking interactions with a different sign.
That is, so I think if you do that in the interactions, then you should also be able to stabilize antiferromagnetic order. If you don't have that, then you will do the opposite. Then you will not, yeah. So if you put it in the, yes, I think I convinced myself now. Yeah. So, yeah, but if you do the interaction in the antiferromagnetic way, you will stabilize antiferromagnetic long-range order. Yes, please.
Can you please describe in the plot between 0 and 1, mean field was used? Between 1 and 3,
So between 1 and 3/2, the solution for the free energy, the exact solution, is not equal to mean field. But the critical exponents, which are only local quantities around the phase transition point, they have the same critical exponents. So this is not a contradiction. You can have the free energies can differ, but the exponent, meaning the asymptotic expansion and the corresponding exponents, are still the same as mean field. Does this answer your question?
So quantum alpha between 0 and alpha positive, you have for field. Quantum EFM.
Sorry, for alpha between?
For alpha positive,
Yeah, between.
transfer field isomorphic, is there an analytical solution for all alpha?
No, I don't. Analytical solution, you mean the free energy?
Exact solution.
I don't believe so.
Then how do we know it's not same? How does one compute alpha?
The usual way to compute things like this is by renormalization group studies. So a much more complicated machinery that is aimed at determining critical properties of that model. You don't know anything, you don't know other properties analytically in an exact way, but you have a way of getting these exponent or sometimes scaling functions at asymptotically around the critical point in an analytic or an exact fashion. Well, exactness, there's always some questions there as well, but this is, so renormalization is the standard way. In the easing case, there was another work where not exactly, well, so there is the belief that the transverse field doesn't make a real difference here because we're looking at thermal properties where thermal fluctuations dominate and not the quantum ones. So you can look at a classical model, long-range easing, and it should have the same critical exponents. So this is all based on these types of renormalization arguments as well. And there is a work of Dyson who shows that the classical easing model also has these properties.
What does the phase diagram look like in the TH plane?
In the?
In the TH plane, what does the phase diagram look like? So.
I think just the. Sorry, the. So, let me do. I think just the usual boring one of magnets. So this is H, and then this is the phase transition line, and it ends at this critical temperature here. I think, but this is, I think, for all types of ferromagnets or antiferromagnets what you have.
But this is the quantum transition.
This is not a quantum phase transition. No, this is the thermal one. This is, we calculated the free energy. This is all thermal properties now. Yeah, I mean, even if it's a quantum model, you may calculate thermal properties as well. Well, it looks like we're going to do the quantum one, maybe not today, but we're going to get to this. Yeah, this is the thermal. Yeah.
So because these statements, I mean, these 3 points, so this phase transition, etc., and the 3, they apply to the transverse field Ising model or to a generic long-range system, classical long-range system with interactions falling off with the power law. Like for transverse field, is there any result for alpha larger than 0?
For alpha larger than 0. So, I mean, exact result, there's always the question what, so, I mean, calculating free energies or partition functions, no. I mean, pretty much, as far as I'm aware, no. For long range cases, well, alpha equals 0 and alpha infinity, but otherwise, I don't think there's any exact result in between.
So these statements is...
But of course, without having the exact solution, you may be able to prove the existence or absence of a phase transition.
So these statements, they apply to the transverse field Ising model or to a generic long-range spin system?
I'm careful with the word generic, but they do apply in much more broadly. But I would not go as far to claim that every model or something. This I wouldn't know.
But definitely for transverse field, these things are established. For example, that if alpha is larger than 2, there is no.
Yeah.
So
and there's also the point where the phase transition vanishes, so alpha equals 0 has been investigated in quite detail, both in the quantum version but also in the long-range classical easing model. And there were a Kosterlitz-Thouless transition that was found at this point alpha equals 2. Yeah, it's so a discussion of the transverse field easing model and some of the thermal properties as well is in this, I think it's 2002 paper by Datta and Bhattacharjee, so the person we were talking about yesterday. Yeah, so I think it's a PRB. Yes.
Large gamma implies a strong singularity at the total point. So in the response is
Yeah.
negative.
Yeah. So.
But the no phase function means no divergence, so this response is weak. So I expect that gamma goes down.
This may well be. So I looked up that there's a linear dependence with alpha, but I did not. Did I see? I'm not sure whether I took the exact figure or whether I did a sketch of the idea that it's continuously changing with alpha. So I'm not sure that it really goes up here, but I would know where to check this. So I hope to answer this then tomorrow. Yeah. Yes.
For generic models,
Yeah.
is the plot qualitatively similar?
Well, so for generic models, it depends on what you mean. If you go to higher dimension, so not 1D, then the phase transition here usually will not disappear. So if you have a 2D or a 3D model, then you will have phase transitions also for larger values of alpha and also for alpha infinity. So you would not have this no phase transition zone. What you would have instead is that you have a region where mean field is exact. It does not always end exactly at 3/2. There are other values for other models between 1 and the dimension between the dimension and twice the dimension. I think it was twice the dimension. I'm not where at some point then it will start to change. And then so let's put here, I think the relevant numbers were dimension, and so for sure this one and the other one, I think it was twice the dimension, not dimension plus 1, but I'm not 100% sure. At this point here, from then on, it takes on, if we have a phase transition also at larger values of alpha, it will be constant again. And this will be the values of the nearest neighbor model, the critical exponents of the nearest neighbor model. So there's the mean field regime for the exponents, the nearest neighbor regime for the exponent, and a continuous connection between them that depends in a continuous way on the exponent alpha. And the exact range where the change happens, so I think it always stops at the same value, but it's where it starts, I believe, depended on the model as well. But I'm not 100% sure about the details, but that is the rough picture at least here.
In what value of alpha this mean field result matches, like not the exponent but the values of the other term? Or does it only match in the mean field?
No, say it again. At what values of alpha?
Yeah, you say that as I am increasing alpha, then like there is a region where the exponent matches, but the transition, like the order parameters or the critical value doesn't match.
Yeah. So match meaning mean field approximation and exact result do not match exactly, but only the exponents match exactly. Yes.
So I think, is there any region in alpha where both matches with the mean field results? Mean field approximation.
No, I mean we have shown that for alpha smaller than d, the free energy matches, so the exponents match as well. So everything matches in that region. In that region, only the exponents match, and then nothing anymore. Yeah.
And can you give me a reference like the second point where can we get that?
The second one,
Yes.
which one?
Like all these results, like second one, phase transition greater than 0 for 0 alpha or between 0 and
A reference for this, where this, so yes. So I give you two references where you then also find more, where really the transverse field easing model is discussed. This is Dota, and I might mess up the spelling here.
And then CHA. CHA double T is
But
get rid of J with CHA. JA get rid of
CH,
R A R J double E. R J double E.
double E,
Double E.
double E. But E, sorry. Now I got it. And it's a PRB, I believe, from 2002, but I'm. Somehow it didn't put the reference here, but and then in spirit, this paper refers to that paper by Dyson saying that because of the argument that for a thermal phase transition, the quantum fluctuations will not influence the universality classes, that you can essentially take the classical Ising model results and then they will apply to the transverse field Ising model again, but they do some extra analysis here as well. And the other paper that does not consider the transverse field Ising model directly, but that is also on this topic is with Michael Fisher as the first author, so one of the giants of statistical physics and phase transitions, and then the other authors are Ma and Nickel. And this is also an old paper, a PRL from 1972. Yeah, so this one here, the PRB, is the one that is most closely, they're saying exactly 1D transverse field Ising model, this is what we're looking at, but then referring to the other papers in any case and telling why these are relevant as well. I think time's already up, so we had a lot of questions. So, I mean, otherwise, I would start now with the quantum phase transition, but there's no point starting it today, so I'll rather stop at this point.
So this